This is a revision video for P6H, Diodes and Capacitors. This is a circuit diagram for a diode. Diodes contain two layers of material sandwiched together. The layers have special properties that only allow current to pass through in one direction. So the current can pass in the direction of the arrow, but if it tries to go back the other way, it is blocked. If we were to look inside a diode, we'd see something like this. We have the two layers of different materials. The N layer, or the negative layer, has got lots of electrons, and the P layer, or the positive layer, has got lots of missing electrons and instead has got positive holes where electrons should be. If the current is in the positive direction through the diode, the extra electrons in the N layer are pulled into the holes in the P layer, allowing the current to pass through. The resistance here is very low. However, if the current is in the negative direction, there are no free electrons in the holes, so they can't move across and conduct the current. The resistance is very high. This is the current voltage graph for a diode. It's got this characteristic shape. As the current is only allowed through the diode in one direction, any current in the negative or reverse direction is blocked by the high resistance. This is the part labelled 1 on the graph. When the current is in the positive direction, it means that the resistance is lower and current can easily pass through the diode. This is region 2 of the graph. Nearly all electronic devices use direct current. The electricity transmitted to your home is alternating current. Converting alternating current to direct current is called rectification, and it's very important as most of our electronic devices do use direct current. There are two types of rectification. Both use diodes to convert AC to DC. You've got half-wave rectification and full-wave rectification. Half-wave rectification is achieved using a single diode. The diode blocks the current in one direction. This produces a series of peaks in the current with gaps in between, as the negative current is blocked. The current is always positive and in the same direction. So we start with the alternating current from the mains electricity. It goes to the diode one way, but it can't go back in the negative direction, so we end up with just the positive left. However, it gives us these peaks with dips in between, so it's not smooth. In full wave rectification, you can combine 4 diodes in a bridge circuit. They are arranged to convert the negative current, or the reverse direction, into a positive one. This produces a series of positive pulses of current, as the negative current is reversed. It is only in one direction, so it's all DC, but it's not smooth, as we've got lots of peaks. So it does need further smoothing before it can be used by some electronic devices. The bridge circuit turns our AC current here all into positive, so it flips all the negative regions into positive directions. The bridge circuit ensures current is only allowed through in one direction. As the input is AC, the inputs switch between positive and negative values. In the first diagram, the top input is positive. So the current's flowing from positive to negative. So if we trace out the path it takes, goes through here, up through this diode, which is okay, so it's going to let it through, out into whatever device we're feeding the current to. Then it comes back round to complete the circuit. It's allowed to go through this diode and then back around. None of the current can go through this diode as it's in the wrong orientation, and none of the current can go through this diode as that's in the wrong orientation as well. So the only way the current can go through here is in this direction. This gives us a positive DC output. Now imagine the second diagram. It's half a cycle later, so now the AC input is positive at the bottom. So if we trace this out again, going up through here, Can't go that way because the diode's in the wrong orientation, but we can go through here. We can't go that way because it's the wrong orientation. We can go through here. This is the same as what we've got up here, a positive output. So that negative AC has been turned into positive output. Then to complete the circuit, we travel through our device, back up here. This diode, the current could flow through there, but then it would carry on its path and continue on and out. The same with this one here. It could go that way, so it's still be forced out the positive direction. So none of the current is allowed to go backwards that way. It's all been forced out the positive end. So we managed to get both AC inputs, so the positive and the negative one, both turning into positive. Okay, just to go over that again and reinforce the important points. The bridge circuit ensures that current is only allowed to go in one direction. The output is always positive. The AC input switches between positive and negative values, as seen in our diagrams here. If the top input is positive, the current can pass through diode A, but it's blocked by diode C. If the bottom input is positive, or the overall input is negative, the current is blocked by diode D, and it passes through diode B, all resulting in a positive output. We're now going to talk about capacitors. Capacitors are found in every electronic device. They temporarily store charge which can be released or discharged later. A simple capacitor is a pair of parallel plates separated by an insulator. This is what's shown on the circuit symbol. Two parallel lines with a gap in between. This circuit has got an uncharged capacitor in it. When the switch is closed, charge will build up on the capacitor plates. The voltage across the capacitor will increase. When the capacitor is fully charged, the voltage across the plates will be the same as the voltage from the power supply. If you disconnect that capacitor then from that circuit, the plates stay charged, or the capacitor stays charged. Okay, so just to recap what we've talked about so far about capacitors, I want you to stop the video and have a try at these questions. If you can't get these questions right, then go back and have a look at the section we've just talked about. Okay, so the circuit symbol for a capacitor, remember, it's our parallel plates or parallel lines. Two devices that use capacitors, well, they are used in nearly every electronic device, so you could have named anything. A TV, a laptop, a mobile phone. What happens to the charge on a charged capacitor when it's disconnected from a circuit? Well, that capacitor will hold its charge, so it retains its charge. If you take your charged capacitor that you've just removed from its circuit and you connect it into another circuit with a conducting component like a resistor or a bulb, then when you close the switch, the capacitor will discharge, and as it discharges, the bulb will light up. So you can see in this circuit, there's no cell or power supply, but the charge from the capacitor is able to light the bulb up. Here are the current and the voltage graphs for a capacitor discharging. You can see that as time goes on, the capacitor discharges and the current falls. It's exactly the same shape for the voltage. As the capacitor discharges, its voltage decreases over time. If the resistance of the circuit is lower, then the capacitor discharges faster. This is because it's easier for the charge to make its way through the circuit. If the resistance is high, then it's going to take those electrons or that charge a longer amount of time to get through that higher resistance. So with a lower resistance, the current and voltage fall away more quickly. If the capacitor has a large charge, it can discharge through your hand or body as an earth conductor, giving you a large electric shock. This can happen if it is no longer connected to the circuit or power supply. Capacitors are used in conjunction with our bridge circuit for full wave rectification. We saw before that the bridge circuit produces these peaks of positive current. Now with the capacitor, they can be used to smooth out that current. So how does this happen? Well, the capacitor is connected as part of the circuit with the diodes. The input AC voltage increases and decreases regularly. When the voltage is increasing, the capacitor stores the charge. So this region, the capacitor is storing the charge. When the voltage begins to fall, so this bit, the capacitor starts to discharge some of its charge. So it keeps the supply more constant. And it's the same here again. As the voltage begins to rise, the capacitor stores its charge. As it begins to fall, the capacitor releases its charge. And it gives us a much smoother supply for all our devices that run off direct current. And that brings an end to this revision video on diodes and capacitors. It also brings an end to this revision section on P6.